Have you ever looked up at a giant building and just thought, how is that thing still standing? I mean, we see these huge towers of concrete and steel everywhere, but we almost never think about the incredible science happening right under our feet. The science that stops them from basically punching a hole right into the ground. Well, today, we're going to dig into that.
All right, let's jump right in with a super specific question. And we're not even talking about some giant 100-story skyscraper. Let's just take a normal 9-story building. How does all of that weight, sitting on what looks like regular old dirt, not just collapse? Well, the answer is a brilliant piece of engineering that's almost completely invisible to us.
So, to really get the solution, you first have to appreciate the massive scale of the problem. We're about to look at the forces involved here, and trust me, they're concentrated in a way that's kind of hard to wrap your head around.
Let's put some real numbers on this. The force, or the load, coming down from just one single column in that 9-story building is about 2,351 kilonewtons. Now, what does that mean? It means imagine stacking 470 cars one on top of the other, all of that weight pressing down on one single spot.
And here's where it gets really wild. All that force, all 470 of those cars, isn't spread out. It's channeled down this one column onto a tiny little concrete base that's barely half a meter by half a meter. We're talking about an area smaller than your coffee table.
So, what happens when you focus a massive load onto a tiny area like that? You get an absolutely incredible amount of pressure. Over 7,700 kilopascals of stress, all pushing down on the soil right underneath. And that number right there, that should be a total disaster.
And this slide puts the whole problem into perfect perspective. The pressure from our column is almost 8,000 kilopascals, but the ground itself, if it's something like soft clay, it might only be able to handle 25 kilopascals before it just gives up. It's like trying to walk across a muddy field wearing stilettos. You're just going to sink. By all rights, that building should punch right through the ground, period.
So, if that little column base can't touch the ground directly without causing a catastrophe, how do engineers get around it? Well, they use a principle that's elegant, it's ancient, and it's incredibly effective. They just spread the load out.
And they do this with something called a shallow foundation. The job of a foundation sounds simple, but it's maybe the most critical job in the entire structure. It takes that insane, concentrated pressure from the column and just distributes it over a much, much, much bigger area. It brings the pressure down to a level that the ground can actually deal with.
Honestly, the best way to think about it is this. It's a snowshoe, right? You'd sink right into deep snow with just your boots on. But you put on snowshoes and you can glide right across the top. A foundation is just a giant concrete snowshoe for a building. Same physics, just a way bigger scale.
And, just like you have different shoes for different activities, foundations come in all sorts of shapes and sizes. You've got long, skinny ones for walls, individual pads for columns, and sometimes you just pour one giant slab called a raft that holds up the entire building. Okay, so we've got our concrete snowshoe. But the next big question is, how big does it need to be? Well, that depends entirely on the snow, or in our case, the soil. You absolutely have to know the strength limit of the ground you're building on. And this gets us to a core principle in geotechnical engineering. There's a technical term for how much pressure the soil can safely handle. It's called the allowable bearing capacity. But really, all it means is how much of a beating can the ground take before it fails. And that one number pretty much dictates the entire design of the foundation.
And check out the difference this makes in the real world. For that exact same building column, if you're building on some weak soil, your foundation needs to be over 4 meters wide. But if you happen to be on really strong soil, you can get away with a foundation that's half that size. This is why you always see engineers taking soil samples before a single shovel hits the dirt. They have to know what they're up against.
So we keep talking about the ground having a strength limit or that it might break, but what does that actually look like when soil fails? It's probably not what you're picturing. Thanks to the work of pioneers like Carl Terzaghi, we know exactly what happens in those moments of failure.
See, here's the crucial thing. When soil is overloaded, it doesn't just get squished down like a sponge. It fails in what's called shear. That means it basically rips apart and flows outwards from under the load, almost like a really, really thick liquid.
And it happens in 3 distinct steps. First, a wedge of soil right under the foundation gets punched straight down.
Second, that wedge acts like a plow, and it forces all the soil next to it outwards and upwards. And third, all that displaced soil has to go somewhere, right? So it pushes the ground surface up on either side, creating this bulge you could actually see. It's called a heave.
Now, this isn't guesswork. This is hard science. Engineers can predict the exact load that will cause this three-step failure to happen. They use these complex equations that take everything into account, the soil type, the foundation shape, you name it, and they can calculate that ultimate breaking point with incredible accuracy.
Now, predicting the exact point of failure is one thing. That's cool. But nobody, and I mean nobody, wants a building that is just barely strong enough. See, engineering isn't about getting right up to the edge of failure. It's about designing with a huge, huge margin for safety.
Because, let's face it, the real world is messy. The soil isn't perfectly the same everywhere. Is it sand or is it clay? Where's the water table? Because water can dramatically weaken soil. All of these things add a layer of uncertainty that you have to account for. And the way engineers handle all that uncertainty is with a simple but incredibly powerful concept, the factor of safety. It's basically a multiplier they apply to their calculations to make absolutely certain the design can handle anything the real world throws at it. So what's a typical factor of safety for a building foundation? It's 3. And that's not just a friendly suggestion. It's a non-negotiable rule in safe design. It's a number that's been proven over a century of building to be the sweet spot. High enough to deal with all the unpredictable stuff, but not so crazy high that you can't afford to actually build the project.
So what does that actually mean? It means engineers calculate the absolute maximum load the soil can possibly take before it breaks. And then they divide that number by 3. And that is the number they're allowed to design for. They build in this huge buffer so the foundation is always 3 times stronger than it ever needs to be, even on its worst day.
And that brings us to the most crucial point of all, the ground beneath our feet. It isn't just dirt. It's a complex, dynamic, and powerful engineering material. It has its own rules, its own limits. And the only reason our cities are able to stand tall is because we've learned, over time, how to understand and respect those limits.
This whole thing is just one of thousands of invisible engineering challenges that get solved all around us every day to make our world possible. It really makes you wonder, doesn't it? What other incredible feats of science are hiding in plain sight, just quietly holding everything together?